Okay, so welcome everybody. Today I will give a talk about statistical micromechanics of dislocations, which is a topic I've been working on for some 15 years. And what I want to do is, of course, define the field micromechanics of dislocations. I will have to define what weak and strong obstacles for dislocation slip means. Then I will briefly rehearse the original Kocks-Mecking model with some small modifications. Then I will discuss the topic of the superposition of hardening mechanisms. And then we go really to the statistical part, first of dislocation percolation, and then we apply it to the grain size effect. These are two theoretical sections. And then finally, I will show some results of the calculations and some conclusions. If we go to basic textbooks, we always see infinite straight dislocations, where you've got here the stress tensor of such a dislocation with its edge components and its screw components. And then you can find also sometimes in the tensorial form the expression of the Peach-Köhler force. And finally, we will have the concept of line tension, where the full formula includes this cosine square psi plus sine square psi, with psi the angle between the dislocation line and the Burger's vector, and a rather mysterious term which has the logarithm of some upper cut of radius divided by a lower cutoff radius, which is closely connected to the dislocation core width. But because this upper cutoff radius is ill-defined, we can as well take all these numerical terms together and say that the line tension is just a constant times the shear modulus times the Burger's vector to the square. And this is then called the isotropic line tension. The tensor I showed you is shown here in graphical form. So you've just got the 6 components of a second rank tensor. But there is a problem with the concept of infinitely straight dislocations. Firstly, there are not enough atoms in the universe to build an infinite crystal. So this is just a theoretical simplification, and the real formulas look a lot more interesting. So we have the Peach-Köhler formula for the stress field of a curved dislocation, in fact, a dislocation loop, where we have to integrate over the entire loop against increments in the length of the loop. This is a very nice expression, of course. We see here, for example, 3 times the Nabla operator, which acts on a distance. And this distance is given in the second formula, where x without prime is a point within on the line, and x prime is a point in the material. So, but in theory, if you can somehow express this equation, you could calculate the stress of a dislocation loop of arbitrary shape in any point in the material. Then we have the formula for the energy of a dislocation, where we've got that the interaction energy between 2 loops, well, in this case, it's the self-energy, because I will take 2 times the same loop, is given by this also very nice formula, where, for example, this second rank tensor T has the following definition, but this Tij, just to write it out, takes more than a full page. And that's a bit the problem with these formulas. You can't handle them by hand except for the simplest cases. And even then, it's tremendous work. But if you can put all these operators in this tensor, if you can generate them by means of symbolic mathematical software, then all of a sudden you can do a lot more with them, because you can't elaborate this second derivative without making a calculation error somewhere. But the computer doesn't make calculation errors. You still will have to define the right coordinate system, for example, for C and polar coordinates, elliptical coordinates. But once it's defined, the computer takes care of everything. And that's shown, for example, by a study on the bow-out of a grain boundary dislocation source. So we've got here a circular dislocation segment which bows out from a grain boundary. But if there was no ledge or no dislocation at the beginning in the grain boundary, then there must remain a dislocation of the opposite side in the grain boundary after the bow-out. So the coordinate system defined is polar. We've got 2 points, one defined by an angle phi, the other by an angle theta. The radius of the loop is r, the width is 2a, and we've got also a coordinate system for the remaining segment, which is along the x1 axis. Of course, the Burgers vector is constant along the entire loop. And then by manipulating Blind's formula in a rather extensive way, we find that the self-energy of such a partial loop is given by this very long formula, where moreover, there appears a big phi over here. This big phi is large transcendent. And I guess nobody of you knows what large transcendent is. I also didn't know it, but the software knows it, and then you can look it up in Wikipedia. So, and that's the big advantage of using symbolic software. The formula goes right down here. We find the self-energy for the straight segment, which looks quite nicer, and the interaction energy between the segment and the arch. Now, another important point we see here, if we use closed loops or finite segments, this upper cutoff radius, big R, doesn't appear. This upper cutoff radius is completely and entirely an artifact of using infinitely long straight dislocations. It will never appear in loops. But the lower cutoff radius is still there, but that's okay because it's related to a physical phenomenon, which is the dislocation core width. And the results of this calculations, for the energy calculation, for example, I put a stream plot, a gradient plot, where a dislocation which starts with 800 Burgers vectors width will follow a path through the energy landscape upward. Once the dislocation can get beyond a certain bow-out length. And then we see that for some dislocations marked by this black line, everything which is below the black line, if it follows the path of greatest energy decrease, will just flow back to zero. So these paths, which follow the gradient of energy, they lead each dislocation that would try to bow out shrinks again. And that's what I plotted here in figure B. You will start with a dislocation with a small bow out, and then the energy evolution is that it will bow out further and then start to shrink. And it shrinks back into the grain boundary. But if we are above the limiting line, then a dislocation will start to bow out. It will also become a closed loop, but a closed loop which is emitted into the grain. So that gives a critical nucleation stress. I also made a second model based on line tension, and you see here the results. What I predict here with the remaining dislocation in the grain boundary is considerably higher than what we find in literature, the old paper by Foreman, Young, and Bayerlein from 2016. They have much lower bow-out energies and bow-out stresses as well. So a second example is circular dislocation loops. To calculate that in a very general way is not really easy, but we can start by only looking at the x1, x3 plane. Then the formula becomes a little bit more manageable. Then you solve for all three components of B separately. So the climb component, the screw component, the edge component. And then to get a general result in any vertical plane, what you do is rotate B, or virtually rotate the dislocation. Yeah, you rotate B, and then you can let the software solve it. The final result is too long to write out. In fact, it's like 8 pages just to express the stress field. But the results are fully analytical, and that means that you can plot and calculate a lot more quickly than what you would do with numerical approximations. So we've got here circular dislocation loops. I think it's just an edge along the x1 axis, so it will become a screw along the x2 axis. And you see nicely how the sign of the dislocation changes along the loop. So we've got all the components of the stress. We also can calculate the self force, the pitch-curler force of the loop on itself to know whether it shrinks or expands. There is the old calculation of Lee and Liu, which is slightly different from what we have here. So there must be in some place of their calculation a simplification or a small error, but in big lines we see the same results. Why did we do it? We wanted to calculate circular pileups. And the pileups can no longer be done analytically, but you can minimize the energy of the system by leaving the radii of the loops free. And you see here in color, we've got the number of dislocations in the loops. And you see that for each number of dislocations, there is in fact an infinite number of stable configurations. So contrary to the classical theory of dislocation pileups, where it is stated that each pileup length corresponds to a single stress. So that's not true. We've got in the vertical axis the yield stress, in the horizontal axis the grain size, and also the relationship is not linear with a slope of 2. It's non-linear, and the slope is not, slope of 1/2, non-linear and variable, well, a higher slope. So the most important conclusion is that the relationship between pileup length and yield stress is not uniquely defined here. So now let's go to the statistics. Well, first, quickly to the strong and weak obstacles. So if we've got a dislocation line pinned on 3 obstacles, which may be junctions, dislocation locks, solutes, precipitates, particles, whatever is in a crystal, then we use this formula. The simple formula for the line tension is equal to the pitch-curler force. And we see that if the dislocation can escape this point, that means if there is a critical strength at which the dislocation can escape, then we call it unzipping. And then we have a weak obstacle with a strength defined as the critical total line tension. But if sine theta is 1, then sine theta can no longer grow, that's the maximum value, then the dislocation will bow out in a fashion similar to what is described in the Frank Reed source. So we can calculate that. This is an idea of Schuck from the 1970s, if I remember. Sada also has touched this problem, but with isotropic line tension. Then we see that the dislocations will not form a circle, but an ellipse. So I still have to correct this term here because it should be done for ellipses. But we've got here a general configuration of a dislocation junction, 2 slip planes, and we've got 2 pinning planes for both dislocations. And what we will try to calculate is whether the total, the sum of these three line tension vectors acts to the left, in this case the junction will disappear, or acts to the right, in which case the junction will grow. That seems to be very difficult, but with this left-hand side plot, it becomes very simple, in fact. Although the plot is a little bit more complex than needed. Firstly, we have to see that it is irrelevant that we have two different planes. The force on this axis, the component along this axis, will always be the same no matter what the rotation of the second plane is with respect to the first one. Then we look at this graph, and the full lines are the ellipses which describe the dislocations. The major axis of the ellipse is parallel to the Burgers vector. Then we've got the pinning points, which is less important. The left-hand side of the configuration is not important. And we find these small ellipses which define the locus of the center of these dislocation loops. And then it follows that the only thing we have to know to look at are these angles θ1 and θ2, which define the point of the center of the ellipse with respect to the reference axis. And what we also find are these outer dashed ellipses, which define bow out. So any ellipse, any point Q2, P2 that is outside of these ellipses will automatically cause bow out. And you can then graph for the classical dislocation logs all possible stable configurations where the dashed lines are is dislocation 1, and the full lines, which appear here as a continuous area, are the second dislocations. So these are the configurations. You can also plot the magnitude or the sign of the, well, I plotted a magnitude, but with positive and negative values in function of θ1 and θ2. And then you find the stability zones of these junctions in any configuration that is coverable by this description. So I didn't work it out further. I've still got one question to answer for myself and maybe for the world. Here we've got dislocations that will grow, and that will move this point to the right. And I still have to work out this equation. What happens to this point? What happens to the ellipse if we move this point to the right while this point Q2, Q1 stay at the same place? But for the rest, this problem is more or less solved. And we find that even the classical dislocation logs have a lot of unstable configurations. So it's not that they are stable under any condition. Okay, now we go to the original Kocks-Mecking model. The original Kocks-Mecking model is described in the classical paper of 2004, I think, 2003, is described as heuristic. And I don't agree to this heuristic description because all the equations can in fact be mathematically founded. So, but for the Taylor equation in its original form, we have to go back to dimensional analysis, which tells us that if a physical process is modeled in terms of n variables, which involve n independent fundamental physical quantities, dimensions, the problem can be expressed by a set of p equal to n minus m non-dimensional variables. So if we want to make a connection between the shear stress, dislocation density, shear modulus, and Burgers vector, then we only got two dimensions, length and stress. So we can express this equation in the form of only two non-dimensional quantities, and we write that in explicit form. Tau over mu is a function of b square root rho. And Taylor didn't want to make things very difficult, so he just wrote a proportionality. It could be, in theory, any other kind of function. And as this proportionality has served us well for almost 100 years, 93 years now, we keep using it. Another equation that is often found is the Orawan equation. In fact, I never found a paper of Orawan where this equation appears. But you can do it in a strictly rigorous and general way. You look at a theorem from homogenization. We define a volume with its loop inside, which has expanded to delta A. So the mean displacement gradient is the integral of the displacement gradient over the entire volume. But by Gauss theorem, you can write 1 over V times the integrals over the surface area of the normal times the displacement at the surface. Well, what we do is we split the loop along the slip plane, and we find that within this area, all atoms have moved by a distance b. So there is a displacement right here, which is constant. Below the slip plane, there is no delta U. And this means that this integral becomes very simple. We obtain that it is just equal to b times the included area. So we do this for all dislocations in the slip system. We sum and we define the slip length, as is the case in the Kocks-Mecking model, as the increase in area divided by the dislocation length. So we do this, we elaborate, we take L to the left, we put that the length in a volume divided by the volume is the density, and the area goes away. We are left with NB, dislocation density, times slip length. Now, this NB tensor, well, this is the transpose of the NB tensor, is this one. And if we take the trace, which would be just the dot product of B times N, that's 0. And we've got here, if we take the symmetric part, we find the Schmidt tensor. So this is the Orawan equation in tensorial form. Here we've got the Orawan equation in scalar form, which will be more useful for the present presentation. If we go to multiple slip, then of course this equation becomes quite interesting. Then the final hypothesis in the Kocks-Mecking model is slip length. So we go again to the pi theorem. We've got two physical quantities and only one dimension. So we find that this function of this non-dimensional quantity has to be equal to 0. But as a function is 0 for all possible values within this argument, and either the function is 0 or it's a constant. So we find that there must be a simple proportionality. There is no other solution possible as long as we don't have any other substructural elements. So if we then put together this one with the Orawan equation, we find that the shear is B times the average slip length times the dislocation density. We derive with respect in both sides. Well, we fill in first here this term, and we find the classical storage term of the Kocks-Mecking model. With a small difference, there is a factor of 2 due to this derivation. Now, the annealing term, annihilation distance, is somewhat more difficult because annihilation will modify the slip length. So we must define the slip length, I put it here plus minus, for storage or annihilation. And we will have along a unit length and plus storage sites and minus annihilation sites. And we know for the equation to be correct, n plus is just the square root of dislocation density over K0, n minus, according to Esman and Mugrabi, and based on the critical annihilation distance, is just rho d over 2 times 2d. Why the 2 is rho d over 2? Because only opposite dislocations can annihilate, so that eliminates 1/2 of the pairs, and then times 2d because it can be cross-slip upward or downward depending on the local configurations. Now of all these sides, the fraction of annihilation sides is n minus over n plus plus n minus. And then we see in the storage equation, we will use now the lambda plus minus because the slip length is shorter in presence of annihilation sides, and not everything is stored. We must reduce the amount of stored dislocations by a factor of 2 times f, because in each annihilation we lose 2 dislocations. So we put on equal numerator, and we find that here these one cancel. Here we've got n plus minus n minus, and we find effectively that the complete Kocks-Mecking model is mathematically founded. Just I had to change the k0 to k1 to make it somewhat simpler. So that's interesting. We can now look what we can do to expand this model. And in the literature, it's classically simply everything is added up. We take a lattice friction, we take the effect of solid solution, which is often put into the lattice friction. We put in a term for the strain hardening. We put in a term for the grain boundary hardening. We can put in something for precipitates and particles. So for example, in this last equations, we got storage, annihilation, grain size. That's up to here, it's the Kocks-Mecking S-strand model. We've got something for the thickness of the sample. We've got something for precipitates. We've got something for twins. And if you want to add other things, if you know other mechanisms, then just sum and sum and sum and sum. And this is, in fact, kind of correct. Let's think about a Taylor series of a function in multiple variables. So then up to the first order, we just find first derivatives. And we can then say, okay, let this function f be the yield strength. F0 will be the Pearl stress. And then x1, it doesn't need to be rho d. It can equally be the square root of rho d. x2 can be 1 over the square root of the grain size. And so we will be able to get a very good fit to most data. But of course, we cannot do interactions between different mechanisms. The empirical fitting parameters cannot be predicted. If we have more parameters, then we have a better fit, but less predictivity, because if to fit more parameters, you need to do more tests, and you may end up with a model which in fact is only valid for a single batch of material. The point is, you can also not extrapolate. You don't know what happens outside your experimental window. So it's nice, it works, it gives good results to publish a lot of papers, but it's not 100% scientific. So I then tried to model dislocation percolation, which was defined in 1966 by Kocks. So we've got here what we call a Poisson point process. All these points are random and independently placed. There's one limitation here. I already put in a grain boundary. The circle of strong junctions, strong obstacles, is a grain boundary. All the other points is a dislocation that crosses the slip field, the slip plane. So, and then bow out happens in this way. Here we've got purely strong obstacles, so we've got only bow out. And you see how the loop slowly fills the entire grain. Well, not entire grain, but a nice part of it. If we increase the density a bit, then we see the loop expanding as well. But it will not occupy so much grain boundary. So now the goal is not to use this for numerical simulations. There is already a discrete dislocation mechanics, but it helps to have an image of what we can do. So we can also put in weak and strong obstacles. Weak ones can be shareable precipitates or the unzipping of dislocation junctions. Strong obstacles would be particles and stable dislocation junctions. And the strong obstacles will contribute to dislocation storage. The weak obstacles will just unzip. We've got here the image. They will go to the dashed configurations, but they don't leave extra dislocation segments in their wake. So that's what we've got here, a very short dislocation. We've got it here, expands to a very big one. That doesn't happen with the unzipping, and therefore the weak obstacles can be treated as a friction term. And of course we have to calculate the magnitude of that friction. Weak obstacles, you can see it here. They are efficient in storing dislocations. At the right-hand side, I use the sinus theta, so an obstacle strength distribution which is uniform between 0 and 1, and you see that there are much less islands within the loop. There are still stable junctions, and there are junctions that are too short or have the wrong angle to let the dislocation unzip. Okay, if we don't want to simulate, then we have to calculate. And luckily enough, there is a single paper from long ago where some of the statistical properties of this Poisson process are calculated. We see that the dislocation segments will be stored almost always on the Delaunay triangulation of this Poisson process. And there is a formula to calculate the circumradius of all these triangles. And from that formula, you can do the statistics of this geometry, which is something I did in 2012. Well, I finished in 2012. I started earlier. An important point to see is that there can be no dislocations with a length longer than this S tau, which is the critical bow out length. So if we are at a certain stress, then all shorter segments will have bone out. And that can then be used to define an evolution equation. The number of segments emitted is the total number of segments still present in the volume times the probability that a segment has this critical length S tau at a given stress S tau times the increment in S tau. Now, this increment in S tau can be calculated from its definition, so the differential can be made. And if we substitute the number per volume by the length per volume, then we find here the density, the derivative of this S tau. We find the average number of segments emitted in a single event, the average length of these segments, minus one of the segments which disappears. This term is not unimportant. Without this term, everything would be much more easy to calculate, but we cannot neglect it, and then the rest of the formula. So I say here, with standard probability calculus and transformation of random variables, you can calculate these unknown quantities. And we find these simple formulas. Again, the thinking must be done by the researcher, but to get these formulas right, to do the integrals involved in the calculations, you go back to mathematical software to avoid calculation errors. This formula, the average segment length, is interesting. It will come back later. The other formulas are just all pulled together in this function k from mu b alpha 0 times the square root of phi c rho d. Now, what is this phi c? We have seen in the animation that we had a dislocation within the slip lane. So, and this will be represented by a fraction phi s in the slip lane. And then phi c defines the fraction of dislocation perpendicular to the slip plane. And even so, only the ones that conform stable junctions. Now, this is a geometrical mathematical equation. It's nonlinear, but it can be solved. And the solution is unique. It is the Taylor equation. And we find a relationship between alpha and alpha zero and these constants and the functions k. It has to be solved numerically because alpha also occurs within the k function. So with that, we really proved that Taylor's assumption was right, but there's another interesting point here in the sense that we can now include a particle density, because while rho d will vary, the particle density will be constant. I just sum in the terms which have rho d. I sum this particle density, I get the rho d to the 3 second out of the equation. I'm left here with phi c only, and k, which now depends also on the particle density. Now, this equation can't be done anymore in an analytic form, and the Taylor equation is no longer a solution of this equation, but you can do it numerically. Now let's go to the grain size effect. So as we saw, everything that reduces the slip length must be taken into account in a statistical way. And the secret here is to take into account that during deformation, the grain area increases. So this can be seen simply oversimplified here in terms of the slip length, the loop reaching the edge of the volume, or by a spherical grain with different dislocation loops which escaped from the grain. They will form small steps of the magnitude of the Burgers vector on the surface of the grain, and what was a sphere which has a small volume area becomes an ellipse with a larger volume area. And the increase in grain area is here given for uniaxial strain, for plane strain. So even at relatively low deformations, the increase is important. So now let's model that in a simple geometry. So we've got here all these elementary blocks which move one dislocation length, and we've got this slip angle. Then, of course, this angle is the number of dislocation at the grain boundaries times the Burgers vector over 2 times the grain diameter. 2 times because we need a step on both sides of the grain. In a real grain, of course, they do not need to coincide in terms of the vertical axis. Then to traduce that to a density, we take this volume, which is sorry. That doesn't matter. And then we can write or find a balance equation which connects the increment of grain boundary dislocations with strain to the increment of volume dislocations, bulk dislocations to strain, which involves the average slip length. So then we repeat what we saw in the annihilation term, just that now we've got a grain boundary here, and so the dislocation starting at x0 can slip to the left, but it cannot pass the grain boundary. So for randomly distributed in independent points, this will be an exponential distribution, and you can calculate the probability that the dislocation that starts at the grain boundary is stored in the bulk, one that starts in the bulk is stored in the interior, one that starts in the bulk and stored in the bulk, this must be PII, and one that starts at the boundary and stored in the opposite boundary, which should be PBB. And again, these are calculations that can be done by hand, but it's always safer to do it by computer. You find all these expressions, which in fact are not so important as a result, but which allow us to go on with our grain size effect. So we use then the balance equation to combine all these results. How it is done, it's in this paper. And what we find is, after some algebra, is that the expression for the mean slip length in a finite grain is surprisingly simple. Coming from here, I was really surprised to reach this point. And then we just put this lambda in the Kocks-Mecking equation, and we find almost the same equation plus an extra term, which involves here the grain size, but without the additional fitting parameter of the Kocks-Mecking Estrin model. And you can use this together with our differential equation based on the density stress relationship, and you have strain hardening particles and the GSE, the grain size effect, into ordinary nonlinear differential equations. So, some results. One interesting point is if we take this probability density function of the segment length, we can get then the probability of a segment length limited by a grain boundary. So let's say the segment cannot be bigger than the grain size. And then we find that the average segment length, the grain size and the dislocation density are related by this dark blue curve. And we see that at a certain point, for example, in 10 to the density of 10 to the 12th, then there will only be a single dislocation within the grain. So we see a transition between a forest dominated, where the segment length depends strongly on the dislocation density. And then we've got a grain size defined part where the segment length only depends on the grain size. So at a certain point, the size of the grain will simply be too small to contain more than a single dislocation. So, and that's something to be aware of. In this grain, it's easier. The number of segments per grain at 10 to the minus 6 crosses here the zero axis. This is logarithmic, so this means one segment. Below that, for a density of 10 to the 12th, it makes no sense to talk about these statistical dislocation mechanisms because dislocations will just run from one side to the other. As the dislocation density increases, then of course we will see an increase in the number of segments. And it is of course known that even in nanometer-sized grains, we can still form smaller subgrains. Now, using the particle terms in the Taylor equation, we find that indeed it tells us what we expect. At low particle densities, we will see no effect at all. And as the particle density goes up, we can predict different curves. The yield strength, the ultimate tensile strength, which I calculated here, goes up sharply once we go over a critical density of particles. And we see also that the uniform elongation, so I recalculated from these curves, gamma tau in logarithmic strains, I recalculated the engineering strains and stresses, and you find effectively the big loss in ductility, which is always observed if the particle density becomes too high. This predicts the tendencies. I haven't found a single paper today where particle densities were systematically varied without varying anything else. So it's very difficult to find a real proof that this works. And even for grain size effect, it's not so easy to find good curves. But I found a few. So here, aluminum 1050, oxygen-free high conductivity copper, and nickel. And I applied my modified Kocks-Mecking model to them, and I find what are, in fact, excellent fits. So you can then look at the yield strength, and there are several graphs here. The black one is just a linear fitting. It's a log graph where we've got here 1 micrometer to 1000 micrometer, and here the shear stress, the yield stress from 10 to 10,000. We find, for example, here the Kocks-Mecking model. We've got here this is the misfit dislocations from Ashby, and the slip length argument from Conrad, which are clearly well below what we measure. Now, the new model and the Kocks-Mecking model were calibrated by the tensile curves we had before. So they both underestimate slightly the effect. We also see that the new model flattens up at very low grain sizes. But at that point, the nucleation model for grain boundary sources takes over nicely. And here in aluminium, we're good down to 10 nanometer. In copper, we're a little below. In nickel, we are a little below. So something is still missing, which probably is indeed some back stress effect at the grain boundaries. There are good numerical simulations suggesting that this is the case. So that should be worked out more theoretically to push this a little bit up. But once we are sufficiently far away from the yield point, then in fact, the predictions are fairly good. So, conclusions. What we propose is statistical micromechanics of dislocations is based on the analysis of the stochastic geometry of random point processes combined with advanced concepts of the linear elastic theory of dislocations. All results are obtained as closed form, first order ordinary differential equations. We can mathematically demonstrate that the Taylor equation and the Kocks-Mecking model are valid. And in the same analytical way, we can extend these models to particle and grain boundary strengthening in a quite satisfactory way without introducing additional fitting parameters. We also found as a corollary that forest-dominated and grain boundary-dominated regimes exist. There is a sharp transition between them. And for the lowest dislocation density, this transition is around 1 micrometer. And the incorporation of weak obstacles, this additional friction term, is something I'm still thinking about. So thank you for your attention.
Thank you, Raf, for a very comprehensive and detailed lecture on the behavior of dislocations and interaction of dislocations. So I stop the recording now. Should stop recording.